Hello, geometry, and welcome to the start of Topic 6 covering quadrilaterals and other polygons. This is Lesson 6.1 on the Polygon angle sum theorem. Now, we talked about the triangle angle sum theorem earlier this school year, where we know that the three interior angles of a triangle add up to 180 degrees. Well, now, what if we explore more polygons? What if we talk about, quadrilaterals, pentagons, hexagons, those kind of things. All right. Okay. So, how does the number of sides of a convex polygon n relate to the sum of the measures of its interior angles? Right. So, convex just means that there's nothing jutting in. Right. Everything is convex. It's I don't know. All I can say is that nothing juts in. So, most of the polygons we deal with are convex. So, let's take a look here at this. Little Savas demonstration here. So notice here that we have a triangle to begin. Okay. So notice that there are three sides, and if there's three sides in your figure, you have one triangle that makes you up, right? Okay. What if I increase this number to 4 sides? Well, now if you have 4 sides, notice when we draw this diagonal, right? If we draw this diagonal, now we've created 2 triangles. If there's 5 sides, notice now if we draw 2 diagonals from one vertex, right, or all the diagonals from one vertex, notice we have 3 triangles. If we have 6 sides, notice again if we draw all the diagonals, 1, 2, 3, 4 triangles. If we have 7 sides, a heptagon if you will. Now we draw our diagonals, we have 5 triangles. If we do 8 sides, an octagon, again draw the diagonals, we have 6 triangles. 9 sides, a nonagon, we have 7 triangles. 10 sides is a decagon, we have 8 triangles. And let's go all the way up to a 14-gon, don't know what the name is, but again, if you draw the diagonals, you have 12 triangles. So here's the idea behind this, this exploration, right? The idea is that your number of sides, n, we're going to make a table right here. The number of sides, which is n. And then over here, I'm going to do the number of triangles. This is really a terrible place to do it. Never mind. Hold on. So sorry about that. Delete that, erase that. Let's do it down here. I'm going to drag this out of the way. Okay. So if I have the number of sides of my polygon, and that's the letter n, and compared to the number of triangles I can break my polygon into. Right? So when I had 3 sides, there's only 1 triangle. When I had 4 sides, there were 2 triangles. When I had 5 sides, there were 3 triangles. When I had 6 sides, there were 4 triangles, and so on and so on. You can see that from the number of sides, if we subtract 2 each time, we will get the number of triangles you can break this figure up into using all the diagonals from one vertex. So from here, the idea is that if you take the number of sides and subtract 2, that's how many triangles your convex polygon can be broken into. And let's recall that each triangle equals 180 degrees, right? Very important. So how is that going to come together into talking about how much the angles in a polygon add up to? Well, let's take a look at the next screen. This is, the Polygon interior angle sum theorem. Let's take a look. It says that the sum of the measures of the interior angles of a convex ingon is 180 times n minus 2. So 180 times n minus 2, that's 180 degrees times the number of sides minus 2. And again, if you think about the last slide, when you take the number of sides and subtract 2, that's how many triangles are in your figure, right? And 180 times that is going to be the sum of all the interior angles. So in this picture, this heptagon, if you add all 7 interior angles, it's going to equal 180 times 7 minus 2 n minus 2. Now let's take a look and explore some regular figures here using Savas, right? I love the explorations here. Okay. So if I take a look, we have, I think, the heptagons back here. Let's go all the way down to 3. So 3, this is a regular triangle, 60 degrees each. So when you have a regular quadrilateral, again, if it's regular, 90, 99, that's 360. a pentagon, a regular pentagon, all the interior angles are 108. That would be 540. For a regular hexagon, all the interior angles are 120, and that would be 720 for the inside. And then back to the heptagon, and there you go. Right? You can go all the way up to a 14gon like we did before. For a 14gon, all the interior angles are 144 degrees, and that's a total of 1440 degrees. Okay, so 180 times n minus 2. All right, now let's take a look at one of these corollaries. A corollary is an idea from a theorem. So this directly relates to the theorem we just talked about. This corollary says the measure of an interior angle of a regular n-gon is 180 times n minus 2 divided by n. This idea here is saying, okay, let's take the sum of all the angles, and since it's a regular polygon, all of the angles must be the same. So just divide by the number of sides, which is the same thing as the number of angles, right? So in this pentagon, if it is regular, that means that angle 1, 2, 3, 4, and 5 are all the same. So let's just find the sum. So this top number is the sum of all those angles. And let's divide by the number of angles, which would be 5, which is also the number of sides. So again, let's take a look at this exploration in Savvis. Again, it's nice because these powerful tools can do so many things so quickly, right? They have these sliders in. So here we go. So not that. Number of sides is 3. So notice, again, that's a bad example, right? For a square, number of sides is 4. 180 times 4 minus 2 divided by 4, that's going to be 90, right? 360 divided by 4 is 90. For the pentagon, 180 times 5 minus 2, 180 times 3 is 540. 540 divided by 5 is 108. And so on and so forth for all. And this time all the way up to a 20gon, right? Man. Okay. So there we go. All right, good deal. So let's see what we have in store next. Ooh, I see a problem. Here we go. Let's take a look. All right, so it says, Jenna is building a corner cabinet to fit in a rectangular room. If she builds it with the angle shown, how can she determine whether the cabinet will fit? Let me move this out of the way real fast. Okay, so this picture right here is a vertical view of this cabinet, right? So it looks like we want to put this corner cabinet in the corner of the room. So the idea here is that, okay, so this corner right here, that's opposite the door, will that fit in the corner of the room? That's the question, right? Can she fit the cabinet in the corner of the room? So we're going to call this X. For it to fit, this must be 90 degrees. So let's determine if it is. Okay, first of all, we have a pentagon. This is not a regular pentagon. It's just a regular old pentagon. And a pentagon has 5 sides. So n equals 5. So to find the sum of our pentagon, we're going to take 180 times 5 minus 2. N minus 2. That's 180 times 3. And 180 times 3 is 540. So the sum of these 5 angles must be 540 degrees. So now we're going to add them up, right? So I'm going to take my unknown angle x. I'm going to add it to 90. I'm going to add it to 90 because there's 2 of them. And then I'll add it to 135, and I'll add it to 135. And this should equal 540. Well, there's only one unknown, so combine the angles you know. So this sum is 450. So x plus 450 equals 540. And let's go ahead and subtract 450 from both sides. And x does equal 90. So woohoo! Because that corner angle is 90, this cabinet will fit in the corner. Yes, cabinet fits. All right, so very good. Thanks for watching video 1. Video 2 is coming up right next.